Wednesday we're going to have a lab.
On Monday we don't have
Reading quiz. Why? All right, so we have, this is the force of the particle as it runs into the wall of the container, is defined by these things. All right? Now, remember this relationship from the first page? That's the frequency, and that's equal to the velocity over the distance that it travels.
Okay.
What's the matter? You're still wrestling with that one?
Yeah, I just need the last part. Like,
Oh, did I go too fast? Negative 2 mvi over delta t. Good. Now, what we just had from the previous slide, force equals negative 2 times the mass times vi over delta t. Well, delta t is some time interval. That's going to be the same as that time interval. So this thing, I'm going to rewrite this, very subtle difference, negative 2 mvi times 1 over delta t. Is it okay? Isn't that the same thing?
Yeah.
Dividing by delta t is the same thing as multiplying by 1 over delta t. Yeah? So I have 1 over a time interval, and this is 1 over a time interval defined by this. This is like the frequency. So I'm going to just plug in this term right here, the Vx over L, into that. And it's going to look like this. Force equals negative 2 mv in the x direction. That's the same as v initial. Good, is the speed in the x direction. Times that which is the same as 1 over t, which is Vx over L. And now I can clean this up a little bit. I have the two v terms. Put those together. It's going to be negative 2m v in the x direction squared over L. So we're just going from one relationship to another, and we're making assumptions, and as long as the gas particles are behaving themselves, these assumptions are good. Like particles, collisions are elastic. We assume that's true. And there's no evidence to suggest that it's not true. Okay, the next relationship, this is all motion in the x direction. That would be the same if the particle were moving up and down or in and out as well. So it doesn't really matter what direction the particle is going. It's going to have this kind of relationship in the other directions as well. Oh, I just have this one other step too. On the previous slide, notice I had that negative sign there. This is the force experienced by the particle. Boom, the particle runs into the wall of the container. And because the container is pushing back on it, the particle experiences a negative force. It's mathematically negative. It's because it's changing direction is the reason that it's negative. Remember how we made that Vf equals negative Vi? Now if we take the point of reference of the wall of the container, Newton's third law says that when the particle hits the wall of the container is pushing back on the particle. If it doesn't, then the particle just goes right through it. On the previous slide, I had force of the particle equals negative 2 mvx squared over L. So if force of the particle is negative force of the wall, that means force of the wall is going to be positive 2 mvx squared over L. Okay, and with that, time to go, guys. 11:44. All right, am I okay to move on?
Is that a plus?
It's plus, yeah.
Look, I have to go. No, it's not working.
It doesn't leave us.
Just take it out.
All right, we love you guys. See you.
Run fast.
So if that force is true in the x direction, then the force in the y direction would be the same exact derivation, and the force in the z direction would be the same thing too. So if we have motion that includes all three dimensions, the x, y, and the z, then we have three vectors, three force vectors. Yes, John. Oh, this is the force that the walls feel, which is the opposite of the force the particle feels. So on that previous slide, I turned it around right here. Force of the particle is negative force of the wall. So we're taking now the frame of reference of the wall. This is what the wall feels. And really, that's the way we measure pressure is what is experienced by the container. So we have an x force, a y force, and a z force. That means that the overall resulting force vector is the x plus the y plus the z forces all added together. Which means that we would take these terms, the one for x and the one for y and the one for z, and add them all together. And when you add them all together, every one of them has something in common. They all have the 2 in common, the m in common, and the l in common. The only thing that's different is what the coordinate on the velocity term is. So that gets kind of pulled out. Well, the 2m and the l get pulled out, and then it's vx squared plus vy squared plus vz squared. Now we have this thing called the Pythagorean theorem. You know the Pythagorean theorem, right? That's one of the simpler things that we do. The Pythagorean theorem says that, we're used to two-dimensional triangles where you have 2 legs and a hypotenuse. But if you have 3 dimensions, like if you have a triangle that's been rotated out into a z-axis as well, then the Pythagorean theorem is still true. It would be the overall v squared. So this is not a negative 2. This is v overall squared. Or that line represents the resultant velocity, considering all 3 of those vectors. Oh, geez. Why? So the overall velocity for this thing is Vx squared plus Vy squared plus Vz squared. And that means we can clean this whole thing up. We can have the force equals 2m over L, that's right there. And then this whole quantity, we can just replace with that, V overall squared. So this line up there above the V means in any direction, the velocity squared. Okay, I have just over 10 minutes left to get this done.
Are you going to every single one?
No.
Oh, but you have to know all of this for the quiz.
Oh, the quiz. That would be neat. I had you derive the ideal gas law on the quiz. There could just be a one-question quiz. Here's a particle in a box. Derive the ideal gas law. Here's that's a great idea. Thanks. That's what I'm showing you how to do now. Just do what I'm doing.
Ah!
I'll let
Why is there a line on
the line on the V represents the overall. It would be like the hypotenuse velocity. You've got an x component, a y component, and a z component, and V is overall hypotenuse, the resultant vector, given those three.
Okay.
So the next thing that we have, now we've established all this physics relationship where we've got force and that's related to mass and the size of the box and the speed of the particle. Now let's see if we can translate this physics into chemistry. We know that pressure is defined as force over area. So again, we're still working with one particle inside of a box. And that particle, as it moves around, bounces into any part of the box, can be exerting a pressure. And that would be the force over a certain area. The pressure in this case would be the force of the particle, which is what we defined on the previous page, 2m over L times the average V squared, divided by the area. So this numerator is force. The denominator is area. Looking at the denominator, is that a reasonable calculation of the area? Remember, the box is a cube with side length L. So one side would have the area L squared, and the cube has 6 sides. So the surface area would be 6L squared. Yeah? That's where I got that from. Now, we can clean this up some. I have an L in the denominator here, and 2 L's in the denominator here. So let's go ahead and fix this up. I got 2 over 6, so that can reduce. It would be this. M average V squared over 3L cubed. Is there something in this expression that we could rename? This box is a cube with length L.